All right, these notes should be for Honors Algebra 2 on Wednesday, January 18th. We have now seen how to shift and reflect functions, specifically in the context of parabolas or quadratics. In this lesson, we will see how to stretch or compress a function in the vertical direction. The first exercise will illustrate this concept with 3 related parabolas. All right, so the first thing we have to do is we have to graph the function given. And I'll do that in red. F of x equals x minus 2 squared minus 9. It says use the calculator to help build a table of values, but I really believe that you guys should be at the point now where you don't need the calculator. You're not going to be able to use the calculator to find points on your test. So the vertex for this parabola is at 2, negative 9. 2, negative 9 is here. So what we want to do now is we want to draw. It really will help if we put in the axis of symmetry for the line that goes through there. There we go. So now we've got the vertex plotted. That's right here. And we can see that the coefficient in front is a positive 1. Therefore, it will act just like the parent. And when I go 1 away, I go up 1 squared, which is 1. When I go 2 away, I go up 2 squared, which is 4. 1, 2, 3, 4. 3 away would be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And 4 away would be 16. 10, 11, 12, 13, 14, 15, 16. The same thing's happening on the other side, and you know this graph is so large, we may even be able to get another point on there. If I go 5 away, I go up 25, and this was 16, so 17, 18, 19, 20, 1, 2, 3, 4, and 5. So there it is. We can get quite a few points on the graph here, and then we just draw the parabola as well as we can. There you have it. There is the function f of x graphed, the leading coefficient of 1, with the vertex at 2, negative 9. So the next 2 things it wants us to graph are g of x, which is 2 times f of x, and h of x, which is a half of f of x. So again, I got rid of part A because I didn't want to use the calculator. However, you could just put that x minus 2 squared minus 9 in your calculator. X minus 2, close it, squared, minus 9. You could graph it. You could see the graph. This table is a little bit different than the one. I want to say it went up to 19 and down to negative 19. So I go to my window. Negative 10 was fine. It's the y values. Negative 19 to 19. You can see that it's going to look pretty close to the graph that we did. Okay, now actually the window, the x's go from negative 14 to 14. There we go. Now you can see it's as skinny as the one that we just drew. Okay, so the next thing we want to do is be able to graph the others. And again, you could have looked at the table from there and found all the points that we plotted. And you can see negative 3, 16, which was on the graph, all the way up to 6, 7. Actually, the next point was 7, 16, which we have plotted right there. All right. So now we're going to do part B, which says on the grid in a different color, create a graph g of x that is vertically stretched by a factor of 2. So 2 times the original. We must multiply all of the y coordinates. Take notice that this 2 is outside of f of x. It is not inside. If it were inside, it would be something like that. It is not inside. That 2 is outside of the given function f of x. So with it being outside, it will only change the y values, and they will be twice as far away from the x-axis as they originally were. So take each point and multiply by 2. All right, so if you look, the origin, this point, or the vertex, that point right there, it is 9 away from the x-axis. If I double that, it'll bring me down to 18. Negative 18. That is my new, the new vertex. This point here is at negative 8. If I double that, it'd be negative 16. And I could do the same thing on this side. Now, what you should notice is the height. From the vertex to this, that height is 2. It is double what this height was. Therefore, you could really find the rest of the points from that vertex. So I could go, okay, if this is 1 over 1 squared is 1, double that, it's 2. If I go 2 away, 2 squared is 4, double that, that's 8. 1, 2, 3, 4, 5, 6, 7, 8. Plotting that point, going up 8 from the vertex. What you should notice is it is the same thing as taking this value, which is negative 5, and doubling it, and taking me down to negative 10. This point is on the x-axis. It's not going to move. So this one will stay. All right, this point, it is 6 above. If I double that, I'm going to end up going 12 above. 1, 2, 3, 4, 5, 6. Actually, it was 7 above, huh? So 14 is where I need to be. All right. So let me erase some of these arrows. Plot the points on the other side. And that would be here. All right. So now I'm going to draw this the best I can. And you see that it is a little more narrow than the function that was given to us before. Any point that did not sit on the x-axis is twice as far away as it originally was from the function f of x. All right, now let's do the next one, h of x. Part C says it's vertically compressed, which means we're going to get closer to the x-axis. It's compressed by 1/2, or sometimes we say that this is by a factor of 2. Compressed by a factor of 2. That is just saying it is twice as close to the x-axis now. So this point here, which was negative 9, is now going to be negative 4.5. 1, 2, 3, 4.5. Okay, so this point here went up, so the vertex has gone up to 4.5. Again, these points are going to stay right on. This point right here was 1, 2, 3, 4. That was 5, so half of that is 2.5. So 1, 2.5. You can see that it's opening up a little bit wider. This point here is, what is that, 8 away, so half of that is 4. 1, 2, 3, 4. So that gives you the first few. Let's go up to this red point. And that one is 7 away, so half of that would be 3.5. 1, 2, 3.5. I could do the same thing on the other side. 3.5. And finally, this one way up here at 16, half of that is 8, which is about here. So here. All right. So I can graph this green one. And you can see that the green opens wider than the other two. All I'm doing here again is multiplying 1/2 by all the coordinates of the y values by 1/2. Could I write all of those points down and just divide the y's by 2? Absolutely. What points did not vary when f was vertically dilated by factors of 2 and 1/2? That would be the x values. The x values stayed the same. They were the same because we had no change to the inside of f of x. The only changes took place on the outside. All right, so in general, vertical dilations of functions, the function h of x equals c times f of x represents a vertical stretch only if c is greater than 1. Understand that if c is greater than 1, then you're taking your typical graph, if c is greater than 1, and you are going to have it be more narrow. If c is between 0 and 1, so that was this case, if c is between 0 and 1, it is going to open wider. Now notice that it says between 0 and 1. It can't be 0 because it wouldn't be a quadratic. And it can't be negative because negative does something different. A negative flips it. But if it were negative a fraction, it would be out here wide. If it were negative a number greater than 1, it would be more narrow, just opening down. And there you have it. So now you can add these transformations to the rules chart, which I don't have open, but I can get that kind of quick. Let's see. Transformations chart. All right, so we've done the first 1, 2, 3, 4, 5, 6 in class, but now we can do this. And when the absolute value of c is greater than 1, it makes it more narrow. And to use the same words, let's go back. And it said it represents a vertical stretch. So we have a vertical stretch. It makes it more narrow. If this is our parabola, it will make it more narrow. If c is a number between 0 and 1, we call it a vertical compression. It's almost like somebody grabs the ends and smushes it down closer to the x-axis. It is a vertical compression. So here, if this is our function, it would open wider. Whoa. It would open wider. All right. These two will come on Monday when I get back. All right. So let's go back, finish these up. So on the back, example 2 says the graph of y equals f of x is shown below. Consider the function y equals g of x defined by g of x equals 3 times f of x minus 2. 3 times f of x minus 2. What you should notice is we are changing it only on the outsides again. So the x values will stay the same. I'm going to take the same gaps from that axis of symmetry, which is here. Okay, I'm going to stretch it by 3 and then drop it 2. Could we write the original function down? Absolutely. If you wanted to, you could go, you know what, I know that f of x equals x plus 3 squared minus 1 because the vertex is at -3, -1. Okay, and now I know that this thing is going to have a vertical stretch of 3 and go down 2. I could put a 3 outside of that. Okay, I could do this. 3 times x plus 3 squared minus 1. Or, yeah, minus 1. And then, x plus 3 squared minus 1, and then minus 2. And see what we get. Watch what happens. This is 3 times x plus 3 squared minus 3 minus 2, which is 3 times x plus 3 squared minus 5. So you can see that the new point will be at -3, -5. The new vertex at -3, -5. All of that is not necessary, though. I'll show you what we can do. Part A says, what 2 transformations have occurred to the graph of f in order to produce the new graph? There's 2 things. One, we have a vertical stretch, and it is a stretch because this number is greater than 1. So a vertical stretch by factor of 3. And then, secondly, it will go down 2. Down 2. All right. So, this point here, the x value is going to stay the same. It was -3, -1. I'm going to multiply that y value by -3 or by 3 first. So times 3, and I get -3, -3. And then I'm going to go down 2. So subtract 2 more, and that'll bring us to -3, -5, which is, let me scroll down so you can see the same vertex that we had there, -3, -5. Okay, you could do that with points, or one better. So right now, I hope we all agree that the vertex of the new function should be right there. The other thing that could be done is we say this. All right, how far away is this point from the x-axis? It is 1 away. Multiply that by 3, and I get 3 away. So 1, 2, 3 away. And now it says subtract 2. 1, 2. That brings me to that same place. Same exact place. All right, let me erase some of this stuff in between. And there we go with our vertex. Now we could see just by that number outside this 3 that everything's going to act just like an x squared, only now it's going to triple. So when I go 1 away, normally 1 squared is 1, and we would put 1 there, but I don't want it there. I want to go up triple that. So 1, 2, 3 away. And I can do the same on this side. When I go 2 away, 2 squared is normally 4. This is 4 away, but now I want to triple that, so I'm going to go up 12. So 5, 6, 7, 8, 9, 10, 11, 12. And just to show you that we're going to get these same points no matter what, for instance, this point here, it's 0 away from the x-axis. After multiply by 3, you still have 0. Subtract 2, and it brings us there. The next point I'll look at is right here. That is 3. If I triple that, it'll go up to 9. Subtract 2, you end up at 7. That is how the vertical stretches work. 3 different ways. So the graph looks like that. Graph and label g of x. I graphed it. Now I labeled it. f of x was this original one that was graphed for us. All right, write the newly transformed function in vertex form. Well, that's what we did at the beginning as well. And I'll scroll back down, but now we know y equals, that vertex is at -3, so x plus 3 squared minus 5, and the multiplier was 3, which is the same answer we got down here. So whichever way you want to go about it is fine by me, but I just want you to be aware of all the different possibilities. All right, I'm going to erase this so we have room to do the last couple problems. Example 3. The quadratic function g of x has a y-intercept of 12. Which of the following is true about the function h of x, which equals something else? Okay, so first of all, it says that g of x has a y-intercept of 12. Y-int equals 12. That is the ordered pair 0, 12. We know y-intercepts have an x value of 0. So now it says what is true about h of x if it is defined as 3 times g of x minus 5. So all of these changes occur outside of the function g of x. I am going to multiply by 3 the y value, multiply by 3, and then, so that's times 3 here, and then I am going to subtract 5. Okay, so the x value stays the same. If I multiply by 3, 12 times 3 is 36. Then all that's left to do is subtract 5, and we get 0, 31. So the other function will have a y-intercept of 31. Moving on to the last one, and that's example 4. On the graph of f of x shown below, a sketch, or in A, it wants us to sketch 1/3 f of x, and in B, 1/2 f of x minus 2. So a couple different things. On the first one, it's 1/3 the original. So all the y coordinates are going to be 1/3 of what they once were. So let's start with this point. It is 1, 2, 3, 4, 5, 6 high. 6 divided by 3 is 2. So the new vertex is going to be 2 high, which is right here. Understand that we have not moved left or right because there is no plus or minus. So I will bring in my axis of symmetry off a little bit, not terrible. And there we have it. So that's our vertex. And now do the same thing with the other points. This point here, 1, 2, 3, 4, 5 away. 5 divided by 3 is 1 2/3. That's about here. The next point, right here, it is 2 away. 2 divided by 3 is 2/3. So that's going to be here and here. The next point, let's see, this one, it is 3 away, but that's -3. Divided by 3 is -1. So its point is going to be here and here. So that new graph, we just say go Pacers, got so many colors up here, is going to be wider. It is 1/3 that of once it once was. All right, now it says what is the vertex form of the transform graph? We would say y equals x minus, actually it's 2 plus 2 squared plus 2, because this vertex, the vertex is at -2, 2. The only thing missing is A, and we know that that is 1/3 because it was 1/3 of what it was supposed to be. And it is opening down. So it looks like that. Negative 1/3 x plus 2 squared plus 2. And finally, the last one. This one's got a little bit more oomph to it, because it wants us to not just change the y values, but for the first time today, we have a change on the inside. It says -2, which is telling us that we are going to go right 2 units. So first thing we're going to do is move this graph right 2 units, and then we are going to do multiply the y values by 1/2, which means we have a vertical compression. Yeah, somewhere in there. Okay, compress by factor of 2. So it's going to be half away of what it once was. So let's first move our axis of symmetry. That wasn't terrible. There we go. We're going to move it 2 units to the right, which brings us right here. So this point that was on it, we've moved it right. It is 1, 2, 3, 4, 5, 6 high. Half of that is 3, which would normally take it right there, but I need to move it right too. Okay, if you'd like to do it in steps, you could. You can move this entire parabola right 2 units first, and then do everything half of what it once was. But that's your call. Okay, this next point right here, 1, 2, 3, 4, 5 high. 5 divided by 2 is 2.5. This point is 2 high. 2 divided by 2 is 1. So normally I'm thinking 1 right there, but I have to move it 2 to the right. The same thing is happening on the other side. Uh-oh. Both of them came with me there. So delete it, and there we go. And there's just 2 more points left that are on this graph. Here's the one. It is -3 divided by 2 is -1.5. But I had to have moved it right too. So there we have it. And there it is on the other side. So as you can see, it is opening a little bit wider, and it is right 2. The vertex form, y equals. It is on the y-axis, so this is just going to be x minus 0 squared, or x squared, plus 3. The only thing is, out front should be a 1/2. And we are done. So now you should be able to do the vertically stretching and compressing quadratics practice, both front and back. And all of these answers, as well as all of the notes that I just went through, they are all on Canvas. So good luck to you, and I have the next one ready for you on Thursday. That's tomorrow. Have a good day. Bye-bye.